So, good afternoon. My name's Nick. I'm a member of staff at EPCC, and it's my pleasure to give you a brief overview of some of the things we're doing and also some of the different things that we're very excited about going forward into the future. So, firstly, to many people, welcome to Edinburgh. We are part of the University of Edinburgh, and Scotland, I think it's fair to say, is a unique country. Bearing in mind the university was founded in 1583, you'd think we were the oldest university in Scotland, but we're not. We're not even the second oldest university in Scotland. We're actually the fourth oldest. But from what is a relative newcomer to the Scottish academic scene, I think we do fairly well for ourselves. I mean, as a university as a whole, we've got about 30,000 students, constantly ranked 20 or 30th in the world, and some of our alumni include Charles Darwin, James Clerk Maxwell, and Thomas Bayes. And there's a rumour, I think Charles Darwin was actually expelled, although the university doesn't really like to publish that very much. So when I'm about to tell you that EPCC has been around for 30 years, in contrast to the university as a whole, 450 years, it maybe doesn't sound that impressive. But I think all things are relative. And certainly in the field of HPC, supercomputing, I think it's fair to say that in the past 30 years, we've built ourselves up as one of the leading centres for high-performance computing in Europe. Now, a number of people in the audience who are long-term collaborators have been a little bit confused this morning or yesterday because they expected to go to where we used to be based, which is on the outskirts of town in a dark, dingy 1960s building. But what's been fantastic for us is in the past year, we've moved right into the centre of town in a brand spanking new building, which is purpose-built. And I'll talk about later on, this is much more than just a move, it's also something very strategic from the university's perspective around computation, around data, so it's hugely important and hugely exciting for us. So we are just under 120 staff across a whole variety of different disciplines and different areas of expertise. And about 80–85% of the staff are based in this building, which is nice and light, nice and airy. I feel maybe a little bit sorry for the other 15–20% because they're in a different building that Mark alluded to before, which by contrast has very, very few windows. So this is our data centre. It's on the outskirts of Edinburgh, just out of the city, and this is where we physically host the machines. So we've got a whole load of different machines here. I've just put on the slide the 8 that I think are most interesting, certainly to me. So the top 4 are our flagship machines. We've got Archer, which is the UK national supercomputer. We've got Cirrus, which is a tier 2 service, so nationally available but a bit smaller. Dirac used for physics throughout the UK. And then what's backing up these systems, and a lot of other systems as well, is what we call the research data file system. And that's a big storage area for scientific data, long term. We've also got a whole host of, we call them local services. I think specialised services is a better term. Things like Ultra, which is a very large shared memory machine we got initially for bioinformatics. The National Data Safe Haven, I'll talk about a little bit later on, but it's all for storing and processing very, very sensitive data. And then a whole bunch of machines for research. So things like this Fujitsu system looking at non-volatile memory in HPC, and also our ARM system looking at the role of ARM as well. Now there's a bit of an urban legend amongst the staff in EPCC, and I've got no idea if this is correct or not, I'm sure Mark will know, that the reason we've hosted so many systems over the years is because up here in Edinburgh we get so much free cooling. Because compared to other parts of the UK, it tends to be much, much cooler. Now, I don't know if that's true or not, but certainly when you look at the PUE figures of these machines, for Archer, something like 1.1 on average, it's pretty impressive. And it's not just the environment, it's also the systems team that spend a lot of time designing the facility and keeping the machines in tip-top condition. And maybe that's especially important talking in the Centre for Carbon Innovation. So for us as EPCC a bit more generally, we're somewhat special because we sit between academia and industry. Because we're pretty much entirely self-funded, what this means is we are not a traditional academic centre, but equally we're not a company, so we're not always focused on the bottom line. Absolutely, we've got to be outward-facing, we've got to be encouraging to work with industry, and we've got to deliver, but we can also bring through a lot of the benefits that being as part of a university can bring. Things like access to world-leading research, development of that research, and also the funding. And so maybe it's no surprise, over our almost 30-year history, we've worked with over 1,000 companies. And the logos of some of these I've put up on the slide, and you'll recognise the majority, if not all of them. And apologies if your company is not on there. You can shout at me later. Now, something that struck me when I was putting this together was the fact that I think it's fair to say, up till about 5 years ago, a lot of these collaborations and this work was driven by computation, so driven by our classic traditional business. Whereas much more in the past 2 or 3 years, there's much more of a data element here, and there's been much more interest from these companies to work with us from this perspective. And I suspect that's very general across our community as a whole, but it's something that's not happened to us by accident. It's something that we've really positioned ourselves towards, embracing data science, but crucially building on all the background and all the foundations that we have in EPCC for HPC. So something that we're extremely excited about and we think is transformative for us in the area is called the City Region Deal. And this started a few years ago when EPCC were invited to provide some input around the role of data, around the role of innovation, to a report that went all the way up to government. And from the back of that and a number of other contributions, Edinburgh and the surrounding region was awarded £1.1 billion of funding, really with the aim of developing the economy and boosting what's already going on here. Now, a very, very large proportion of this is around data-driven innovation, and a big part of that is EPCC and what we're doing. And sort of the master plan, if you like, is this diagram on the right here. The overall aspiration is to make Edinburgh and the surrounding region the data capital of Europe. And the way they're looking at doing this, really at the core, is to have this idea of what's called the world-class data infrastructure. I'll talk more about that in a second, where they've got data storage, data analytics tools, but then you've got a whole host of people with the skills to analyse that data, to process that data, and they actively look outwards to companies in a number of different fields, looking at trying to transform what they're doing. And we promised over £5 billion of economic benefit for doing this. So the pressure's on. Now, what I think is nice about this is quite often you see a diagram like this, and it's very much aspirational. And you say, yeah, right, but is it actually going to happen? Whereas actually here, there's real-world big sums of money behind all of this. So for instance, this world-class data infrastructure at the centre, that's something that we're very largely responsible for. There's a lot of money behind that, and I know Mark later on is going to talk about some of the work already on the facilities side supporting this. I mean, one of the challenges of this is procuring a system and a machine that can be all things to all people across all these different sectors. So the past 12 to 18 months, we've been doing loads and loads of pilots, loads of experiments across lots of different areas, lots of different companies, drawing tons of diagrams like this to really understand what the system looks like. Because we've got data somewhere in lots and lots of different formats. People want to work with that and generate insight and then consume it in lots of other formats. And the key question is how to hook all these together and where all the tools sit and where the technology sits for here. And it's even more complicated than this, because talking to lots of different people, the data sets themselves are very, very different. You know, some are very, very open, happy days, whereas some are very, very sensitive, very private, but people still want to exploit this, still take advantage of this, and get the value from that. So how on earth do we have an overarching system that can keep all these different people happy and give all the security and give all this governance? And the good news for us is we've got Fulhame here. Because for the past, I think, 4 or 5 years, we've been managing what's called the National Data Safe Haven. And what this is managing all the data, all the health data in the Scottish NHS across Scotland. So just over 5 million people in Scotland, whenever they have a medical procedure, all that data is stored and at some point enters this system that we house and we manage. And that's this red area, the red zone or the identifiable zone. And this is just so sensitive because it's unconsented data. They haven't given explicit permission for people to work on that, but it's for the greater good, and that's the policy that's laid down from on high. Now, what researchers can do from the other perspective is they can say, right, I want to work with that data, I will write a proposal, and if that's successful, they get given a very tied down, very specific virtual machine. Now, they can't, for instance, get my individual data or your individual data, but what they can do is they can generate statistics behind the scenes around populations of people. So they might say, well, give me that statistic, and that statistic, I don't know, from every male over 50, from a specific ethnic group, which has a specific health condition. And then from that, tease out these different patterns and try and understand what's happening and try to understand some of the mitigation we can put in place. As I say, very, very sensitive from the security side, but also all the engineering to provide from the infrastructure side, the storage, the performance, all this different querying. So that's very much, I say, the data engineering, supporting these data scientists, exploiting the data and getting value from it. Something we've found, again in the past 2 to 3 years, much more growing for us, is the data science itself. Working with companies, exploiting their data and being able to give them insight on what they've got already in the business. And we're doing lots and lots and lots of this. I just wanted to give you one brief example that really summarises this whole host of different projects that we've got ongoing at the moment. Because we've just finished a project with an international company in oil and gas called Rock Solid Images. And one of their products is selling what they call well atlas information. So ships come along, they collect lots of borehole data, and this is then refined into a higher level view of the well, such as the mineralogy composition, whether there's oil or gas, etc., and that's what they sell. The big problem for them, and the problem that they came to us with, was they've got all this raw data of wells, but it's 7 days of manual effort to convert that into a single well atlas. And they've got like 20,000 sets of raw data for wells. So they estimate something like 200 years of effort to generate all these well atlases, which just isn't realistic. So they said, look, what we're fundamentally doing is pattern matching. Is there a role for machine learning here to help? So we used the latest and greatest machine learning techniques, and they do work, but with some really important caveats. So just to give you some highlights on this. On the left, what we've got is the vertical is the scale from the seabed at the top all the way down by meters, and at the bottom is porosity, fraction of porosity. And we've plotted the truth, their interpreted value, which this specific thing takes many hours to determine. Whereas the prediction, once our model is trained, is a fraction of a second. And on the right is what I call the moneymaker. And this is where we've got some fluid in the rock, but they don't know if it's water, which is bad, or if it's hydrocarbons, which is good. And they're looking at categorizing that. Yeah, good is a relative term. They're looking at categorizing that and really understanding that. And again, their truth interpretation on the left that they've spent a lot of time with, and our prediction that we generate very quickly, sight unseen, on the right. Now, it's not a silver bullet. If you look at these closely, they don't fully match, but they give them a really important starting point to be able to then move forward from. And so they estimate this reduces the time from about 7 days to about 2 days. There's still some work to be done here, but still, that's a really important thing for them commercially to progress on that. I must admit, I was actually really shocked here. And I was really shocked here, and it's a lesson I've learned, that actually behind the scenes, these frameworks, taking advantage of our HPC machines like Archer, our Cray, are terrible. When we started, it took like 48 hours to train the model. And with about half an hour's effort, we got that down to like an hour. And I think that's really important for us as a community, as a lesson to learn here, because there's such a role for our knowledge and our experience to support the future of data science. And this close collaboration, I think, is going to be critical on state-of-the-art supercomputers like Archer. Now, on the topic of Archer, this has been a huge success for us, the UK National Service. And it's one in the latest of generations that we've hosted over the years. It's actually a pretty old machine. We've had it for 6.5 years. When we turned it on, it was 19th in the world. It's now over halfway down the top 500 list. So maybe it's not a surprise that come the start of next year, it's going to be decommissioned, and there's a new machine that's going to come in, a new national service which we will be physically hosting as well. So we're very excited about that. But that's not to detract from the benefit that this machine has brought. I did some calculations the other day, and I've calculated, there or thereabouts, when we turn this off, this will have done around about 7 billion core hours of computation, which is a crazy amount. It's something like 700,000 years of computation. Maybe a little bit more importantly, yesterday a few of us were looking on Google Scholar and trying to figure out how many citations have come from this. And we can find over 1,000 that either directly acknowledge the machine or at least mention that they've used it. And when we relax the term a bit more, we start to get lots about archery and bow and arrows and stuff. So I think beyond that, there's quite a few false positives. But yeah, loads and loads of things have come from this. And as well as the fantastic work done by our systems teams, also what's been really important is the fact that we've put a lot of effort into the user support, the documentation and the training, but also the Research Council, when they installed this, put aside a big pot of money to work with codes, porting them onto this machine. So over this period, over 65 codes have benefited from fairly short projects to look at the code, look at optimizing it, and getting it onto this machine. And this has been fantastic for us in EPCC, for the wider HPC community in the UK, and we've just done under half of these 100 projects, getting them on here and getting them taking advantage of the power that we can afford. So what I want to do now then is switch gears a little bit, because I want to talk about a project which is very large that we've had funded fairly recently, but we're really, really excited about. And that's really looking towards the future, looking towards exascale. And that is what's called the Asimov project, which is a collaboration between a number of universities and a number of companies. We lead it as the academic partner, and Rolls-Royce lead it as the commercial partner. And the overarching aim of this is, for the first time ever, to be able to do a high-fidelity simulation of an entire gas turbine jet engine. Now, that sounds easy to say, but in reality, it's way, way, way more difficult to do. I mean, I think this is the Trent 100, and it's just so complicated inside, all the different moving parts, all the different temperatures. But potentially, if you can crack this, there are massive commercial benefits for doing this. Now, one of the reasons I think this is so fascinating and so exciting is because, we talk about exascale, and quite often people say, yeah, but if we gave you an exascale machine, would you have the codes to be able to use it? Well, this is a use case where absolutely we believe we would. Because what we estimate is, if you could give us an exaflop, the resulting simulation we think would take about a day. So actually, we'd like 4 or 5 exaflops. Furthermore, we think there's about 1 billion core hours to do this simulation. So if you think something like Archer, our current generation national service that we're going to decommission, that's about a year of pure computation on that machine if you had perfect scaling. So, it's a vast, vast challenge here in terms of the scale of the computation, the scale of the data, and all the different bits that we're looking at and trying to solve. And that's why it's not just us and Rolls-Royce. There's actually a lot of partners here over this 5-year project. I say we're the 2 leading partners, but also a number of other universities, a number of other companies bringing some really, really important key skills into here to make that big picture, to solve this grand challenge and the associated challenges with that. And there's a whole host of things. It's the computational method, but also the raw parallelism. How on earth do you expose that amount of parallelism and leverage it efficiently? And in doing that, we're building on many years of research projects that we as EPCC have been involved in and continue to be involved in. And that's some of these projects up here on the screen, many of which come from EU funding, which are either looking to develop HPC parallel technologies specifically themselves, or leverage existing technologies within the context of codes that are already out there. And so what I want to do is just dive into a couple of these things and to show you a couple of the things that we think is really exciting and interesting as it currently stands in 2019. So the first of these is a machine that we've had for just over 6 months with 4,000 cores of ARM. So this is Marvell Thunder X2, and it's funded through the Catalyst UK programme, which is looking at further maturing and developing the ARM software ecosystem for HPC. So this is a fantastic test bed for doing that, for exploring with all these different things and giving people access to this. They can play with their codes and see what they're getting on this architecture. I just want to give you a flavour of the couple of things that we've done on this. So for instance, one of my colleagues, Adrian, who's just sitting over there, and when the machine was really brand spanking new, he took a number of the different codes that are quite popular in the UK, so that's this thing here, and compared them against those codes then running on more traditional x86 systems. Really looking at the performance that we can get out the box, but then naturally it's, well, okay, why are we getting the performance profile that we are? And then let's look at actually the methods and the techniques to optimize these and really get them singing on the architecture and working well. So that's one big area of focus that we've baselined and benchmarked, and we're pushing forward on this and looking at this. Another area, for instance, this is something I did a couple of months back, looking at the relative performance of different MPI implementations on the machine. So this is the HPCG benchmark, and what was really interesting is on x86, MVAPIC tends to work really well, but there's clearly something not quite right on our ARM system, because in comparison to these other implementations, it's quite a bit slower. So we were talking to the folks over in Ohio about this, and they know exactly why it is. We've then given them access to the machine, and they're now working with us to improve this and optimize their library for this architecture in order to be able to push this forward with all the other bits and pieces. So that's one thing we're looking at, really the role and the whole ecosystem around ARM in HPC. The other thing I wanted to briefly mention is looking at the role of non-volatile memory in HPC. So this is a big European project that we've led, and if you're not so familiar what this fits into the same slots as DRAM. It's slightly slower than DRAM, but much faster than hard disk and SSD, but crucially much larger than DRAM, and it's persistent. You lose the power, the data's still there. So based on those properties, well, actually, how can we most effectively leverage this going forwards? Because Intel and other companies are absolutely making this and manufacturing this. So Fujitsu, as part of this project, built a bespoke system for us with this non-volatile memory in. Globally throughout the system, we have just over 6 terabytes of DRAM, but 100 terabytes of non-volatile memory. And we in EPCC have really been exploring these different use cases. So one thing, for instance, very briefly, is CASTEP, which is a very familiar code in the UK with different usages. It's known in many cases not to scale particularly well, especially for some of the DNA work. But you've got to do that because you hit memory limits. And the memory limit here is 1.7 terabytes. But with this system, we've got 3 terabytes per node. So actually, we can keep it on node much, much longer and avoid these overheads much, much longer. And yes, there is a little bit of an overhead of doing this, but for these sort of codes that are limited in that perspective, it's not a massive thing potentially compared with going distributed. Another thing is, can we use this non-volatile memory instead of the file system? So this is OpenFOAM with a CFD example, and what we're doing here is comparing loading the data in from the file system and processing it, compared with it's already in this non-volatile memory, and we're just going from there straight away. And as we increase the number of nodes, you see the benefit of this increases. So on 16 nodes, 8% faster if you use this non-volatile memory, and 20 nodes, 25% faster. So looking at all these benefits and all these different things. Of course, what this then produces is, okay, well, how can I make my batch system clever enough that it will know this locality and it will handle this when it schedules things? But if you're interested in this, Adrian, one of my colleagues, will be at SC19 giving a tutorial all about this, and he promises it's going to be super duper awesome. So not my words, his. The very last thing I want to talk about, just within my last couple of minutes, is some of the training that we do here, really on the topic of tutorials and whatnot. Because in EPCC, we've run an MSc program for the past 18 years. And this has grown from strength to strength year on year. So these are some of our MSc students from years past. About 5 years ago, we diversified. So we went to a second program, not just straight HPC, but also HPC with data science. And this year is a record year for us. We've got 70 students, so it's about double what we had last year. And they've all just started a couple of weeks ago. And until about April next year, they take a load of our different taught modules in our community, in data science, and then towards the end of the programme do a 3-year dissertation. And really it goes back to what I was saying before, in terms of our links with industry, the fact that a lot of these are industrial dissertations, and the industry loves this because they get some free effort, and the students love this because they work on a real-world problem. We've also had lots and lots of PhD students over the years, and I think we've got 6 at the moment when I counted up yesterday, across very many different areas, and then some miscellaneous training as part of delivering the services and our other commitments. Related to this, the last thing I wanted to talk about, because it is quite a big part of what we do in some areas, is public engagement and outreach. So what we do, we have certain members of staff who go out to local schools with different activities to encourage the kids and engage with them in the field in general. But also what we've built is something what we call WeArchie, where we've got a Perspex case and we've put in a whole load of Raspberry Pis. So this is 64 cores of ARM that we take to different conferences, different events, and people can actually design an aircraft wing or put in flood defences, and within a couple of seconds it will simulate it and they can see the results of what they've done. It's actually really annoying how well this works. Because, as a researcher, we do so much clever stuff, so much hardcore stuff, but they all want to talk about this. And, these Raspberry Pis and how we've put it together. And we've had this all over the world. So this was me with it in Boston in the US at AAAS a few years ago. So it's been something that's really successful and worked very well for us, and we've shared with people further afield as well. So thank you very much for listening. I've just tried to give you a brief overview of some of the things that we're doing and some of the things that we're really excited about. I've scratched the surface, so if you've got any questions or you'd like to discuss things more, please speak to me, one of my other colleagues. And with that, I'd like to say welcome to Edinburgh, and I very much look forward to hearing the other talks over the next 24 hours.